So in this problem, we're told a skier traveling 9 meters per second reaches the foot of a steady upward 19-degree incline and glides 12 meters up along this slope before coming to rest. What was the average coefficient of kinetic friction? So in order to solve this problem, first we got to understand what's going on. So we have this guy, he's going to reach this bottom of this incline, and we know he's going to be traveling with 9 meters per second. He's going to travel 12 meters up this incline, and then his velocity is going to become 0. And so we're also given the degree of the incline, which is 19 degrees. And they tell us we're going to be solving for the coefficient of friction. So we're going to be solving for the coefficient of kinetic friction because we're going to be moving here. And so how are we going to do this? So the way we're going to do this is by using the law of conservation of energy, which basically tells us the energy at one point has to be equal to the energy at another point. So we can say E1 equals E2. Now, when we talk about this, we're talking about two types of energy in this case. Kinetic energy, which we can denote by K. So K equals 1/2 mv squared. That's the formula for kinetic energy. And the formula for potential energy, which is denoted by U, is mgh. So the kinetic energy plus the potential energy at one point is equal to the kinetic energy at another point plus the kinetic energy, or the potential energy at the end. So the beginning has to equal the end. But there's another thing you have to take into account in this case. Since there's going to be energy lost due to the force of friction, so as we go up, there's going to be work done against the person traveling up. So we also have to add over here, or we can subtract it or add it. So you can subtract it initially. You can imagine we have this much energy, but we're also going to lose some energy as a result of friction, and that's going to equal our energy at the end. So hopefully that makes sense. So we have to include subtracting the work due to friction. So you can call it minus WF, and you can add it to this side because basically it's the same thing, but I think it's easier to imagine that you have your initial, you lose some energy, and that equals your final energy. And so this is going to be the basic idea of how we solve it, and we're going to plug in certain values to be able to solve for mu sub k. So let's go ahead and get started with that. So I think it's first easier just to see, or to draw the free body diagram that's going to be acting on our person here. So we know that we have the normal force going up. We know we're going to have the force of friction acting opposite of the way of travel. And then we know we have the force of gravity acting straight down, which is mg. And then this mg is going to have two components. Fg of y, which is in the y direction. We consider this to be the y perpendicular to the plane. And then the x is parallel to the plane. So just keep that in mind when I refer to that. And then Fg of x would be right here, parallel to the plane, so in the x-axis. Those are going to be the forces acting on our person. And now what we're going to do is solve this equation and get it in terms of the variables that we actually need. So K1 is the initial kinetic energy. So 1/2 mv1, we'll say, the initial velocity squared, plus U1, which is its mass, times gravity times its height. So plus mg, those are constants, and then H1. Minus, and then WF. So the formula for work equals force times distance. So in this case, what is the work being, or what is the force being applied? So we're talking about the work as a result of friction. So the force of friction is our force here. We know the force of friction, the formula for it is mu sub k times F sub n. And then still multiplying by the distance. And then mu sub k times F sub n times d, we need to find what F sub n is now. So in order to find F sub n, what we're going to do is sum the forces in the y here. So if you sum the forces in the y, we know the sum of the forces in the y are going to be equal to 0. Because this is equal to may, so the mass times the acceleration in the y, you should know acceleration in the y is 0 if you don't move in that direction. We're only moving along this x-axis here. We don't move in this direction here. So this is a of y is 0. Sorry about that. So this value is just 0. So 0 is going to be equal to, and then we just add up the forces in the y. So the normal force, and then we also have Fg of y. Those are going to be the two forces in the y. These are all in the x right here. So we have F sub n. If it's upwards, I denote it as positive, minus Fg of y. So F sub n in this case is equal to Fg of y. And then how do we find Fg of y? So it's going to be the y component of this gravity force. I can show you how we find it. So if you imagine this triangle right here is this triangle, the same thing. So this right here corresponds to this side, which is mg. This is your fg of y, and then this is your fg of x. This angle right here is the same as this angle, and you should know that this angle corresponds to this angle of the incline, to the same value. So this is 19 degrees. So if you want to solve for fg of y, you would use your cosine function. The cosine of an angle, in this case 19 degrees. Cosine is adjacent to the angle, which is this side, over the hypotenuse. So fg of y over mg. If you multiply both sides by mg, you'll get fg of y by itself. You'll find this mg cos of 19. So you have fg of y, which we said was equal to our f sub n, right? Because f sub n equals fg of y. So we have f sub n is equal to mg cos of 19. So all we did was sum the forces in the y, and then these two equal to each other. So we just found out what fg of y is. So now we can just go ahead and plug it in. So mu sub k times mg times the cos of 19. And then you would multiply that by the distance. In this case, we travel 12 meters. That's how long the force is being applied for. So this would be 12. So we're minusing mu sub k times mg cos of 19 times the distance. So all we did was find out the work due to friction, and then we just plugged it in. So this is going to be equal to 1/2 mv final squared. I'll just call it 2 actually. 1/2 mv2 squared plus the potential energy mgh2. And now we have our equation all written out, and we're going to cancel some variables here. So what you should notice is the height. When we choose it, we can choose it to be any point, but I'm going to choose it to be right here. So we're assuming this height is 0, right where the person starts. So at this point, the h is 0. So we know that h1 is going to be 0 because we can basically choose that. So if this value is 0, this whole thing goes to 0. We also know the velocity at the end is 0. They tell us at the point which we're going to is 0 meters per second. So if this v2 is 0 at the end, this whole term goes to 0. So now we have v1 squared and h2. So we know the initial velocity they tell us is 9 meters per second. Notice we don't have the h2 though. So how would we find that? So we need to know the height at which it goes to. And the way we're going to solve that is by using the triangle here. So notice this is our triangle. I'm just going to redraw it like this. We know this length is 12 meters. They give us this is 19 degrees. And we want to solve for this side, which would be the height, right? This would be how far we travel up relative to here. So we need to solve for the h. So notice that it's equal to the opposite, or we could use sine to solve for this. So the sine of an angle, in this case 19, is opposite over hypotenuse, h over 12. And then you would multiply by 12, solving for your h. And then I'm just going to solve this out. So 12 sine of 19 is 3.9. Yeah, 3.907. So now we have h, and we have every variable to solve for mu sub k. So we have the v1, we have all these variables, so just a matter of solving now. Notice that there's a mass in each term, so we can cancel that to make it easier to solve. So mass, all these cancel. So if I rewrite it over here, we have 1/2 v1 squared minus mu sub k times g cosine of 19 times 12. And this whole thing is going to be equal to gh2. So now I'm just going to plug in the values. So 1/2 times v1, the initial velocity is 9, 1/2 9 squared minus mu sub k, which is what we solve for, times g, acceleration due to gravity. This is just a constant, 9.8 meters per second squared, times cosine of 19 times 12 is equal to g, which is 9.8, and then multiplying by h2, which is the height we end at, which we just solved for right here. So 3.907 meters. And then now I'm just going to simplify and solve. So 0.5 times 9 squared, which is 81, you get 40.5 minus, and then 9.8 cosine of 19, and then multiply that by 12, you get 111.19, we'll say, and then this is times mu sub k is equal to, and then we have 9.8 times 3.907, which is 38.2886. So now let's go ahead and solve. So I would minus this to the other side. So keep in mind that this is minus 111.19 mu sub k equals, so we have 38.2886 minus 40.5, which is minus 2.2114, and then just divide right here. So dividing, so divide this by minus 111.19, and you will get mu sub k is equal to 0.019888. So about 0.020, or however you want to round it, doesn't really matter, but about 0.02 is going to be your coefficient of kinetic friction. So when they ask for, they're just asking for the average coefficient of friction, it's going to be about 0.02. Keep in mind it's unitless because we're talking about the coefficient of friction. But yeah, so all we did was use the law of conservation of energy, but we also had to account for the work. So just keep that in mind. If you have another force acting on it, you're going to have to include that in. But yeah, so this is going to be your answer right here, 0.02, and hopefully you found this useful.